Not really. Okay, lesson 9.4. This is lesson 9.4 help. I'm just going to go over some of the questions. I know 8, 9, and 10 are ones I'm definitely going over. Since the first 6 are pretty straightforward from the formulas, and I'm not going to go over those, you omitted number 3. Number 4 is, the only thing you need to make sure that you did on 4 is, since it said the populations are the same, is you set these equal to each other. Okay, and so that's it. And then because you have variables, where are your variables located? Up in the exponent. So how are you going to get them out of the exponent? Yes, you're going to take the log, and because you recognize that there's an e involved, taking the natural log and pull that down and all that. Also, the only thing about 5 and 6 is that it gives you this thing. When will it be double that? And so you know that the population initially is at 6 billion. When will it be double that? And so that's going to be your 12 billion here. It's growing continuously, so I have an E model. And then your rate is up here, and your rate is a decimal. Okay, and then you're going to solve that. Are you going to natural log both sides right now, or are you going to do something before you natural? Yes. Divide by 6 first before you natural log both sides. You go, girl. Okay, so let's go on to the 8, 9, and 10 that you guys wanted to get help on. Okay. So we're putting an 80-degree soda into a cooler. We know that we have this model here. Now, is this realistic? No, but this is a sample of something that you might have later when you're talking about a rocket and some jet fuel. I don't know, you know, because you're all going to go be rocket scientists. So when this first one says evaluate f of 30, f of 30 is saying what? Correct. That is stating, that's just function notation, stating that t is 30. So you're going to evaluate this by just putting in a 30 for t. So your answer is going to be 32 plus 48 times 0.9 to the 30th power. Once you evaluate that, then, I'm not telling you that answer right now, but when you evaluate that, what does it say? What is that telling you?
The temperature after stability limit.
Correct. So what that's telling you, what that answer means, is that would be your temp after how many minutes? Because it defines for you, good, 30 minutes. All right. B is saying how long will it take the soda can to cool to 50 degrees. Well, this is representative of your degrees, your function f of t. So all I'm going to do is what? I think we can set that up. Correct. So plug in 50 for your end result, and you got 32 plus 48, 0.9 to the t. So we're solving for t. You're going to have to use logs to solve that. And I'm not going to finish solving that out for you, but that sets it up. Okay, next, I really like this question part C. Common sense tells you that you cannot cool down the can to 30 degrees. Why does common sense tell you that? Good, because that's lower than the cooler itself. So yes, common sense tells us that, but let's confirm that. How could we confirm that and show that that's not possible? Correct, exactly. If I'm saying I want my end result to be 30, and then I have my function, and what happens is when you start solving this, You know, and you're subtracting 32, and then you're dividing by 48, and all that kind of stuff. I'm not finishing out everything here. Okay, and then you're going to log both sides. So what I end up having is negative 0.0417 is 0.9 to the t. Logging both sides to get this, solve for this variable. What does that then place within the log?
Negative.
Yes, that's placing a negative within the log, and because that is outside of our domain, that's over here somewhere, that's not real. So that is why it is impossible. So that's mathematical description of why it's physically impossible to cool that down. Okay, number 9. A confused student insists that log x plus y is equal to log of x plus log of y. Create an example to disprove this misunderstanding. Right, you just pick a value for x and y. And so any, just, randomly pick a value for x and a value for y. And so say you do 2 and 3. You're just going to see if log of 2 plus 3 equals log 2 plus log 3. And then you're going to put those in to your calculator, and you're going to see that, no, those two amounts do not equal each other. And so then, therefore, all you had to find was one example that was wrong to disprove his belief. So you need to go ahead and get your calculation here and show that those two sides are not equal to each other. Okay, number 10. Number 10 is talking about the relationship between an airplane's weight, x, and the runway length at the time of takeoff. So this runway length is in thousands of feet. Okay, so this right here is in thousands of feet, and that's the runway length. X is the weight of the airplane. So this is length in thousands of feet. And this is the weight. Okay. If the weight of an airplane increases tenfold from 10,000 to 100,000 pounds, does the length required for the runway also increase by a factor of 10? Support your answer. So how are you going to approach that? You're going to what? Set and fold. Exactly. Do both of those equations and see if one of them is 10 times the other. So, because this is 10,000 pounds and this is 100,000 pounds, then what I'm going to do is put that in. I'm going to say, here's my one for the 10,000 pounds. Okay. And here's my one for the 100,000 pounds. Okay, so this would tell me the length of my runway for a 10,000 pound airplane. That was needed. This would tell me the length of the runway for a 100,000 pound airplane. And what are we trying to see?
If it multiplies the runway.
Good. If this one times 10 is equal to the other one.
No.
Well, yeah, because if you end up calculating that out, you're just seeing if, yes, so like this one ends up being 12, and this one ends up being 15, and no, 12 times 10, is not 15. So no. And if you think about graphically what's happening, here's your say this is your, right here is the 12,000 length runway, and that's for a 10,000 pound airplane. And this one right here, 15, that's way out here, and that's for a 100,000 pound airplane. So graphically, that's what's happening. Because this rate is so gradual, that's why it's only a little bit of height, a little bit of difference for that big of a weight difference. Okay. B, estimate the maximum weight of a plane that can take off from a runway that is 10,000 feet long. Remember that our length of the runway was in thousands of feet, so 10 equals 3 log x, and all you're doing is solving for x. And I don't want to put 10,000 here because the equation said that is in thousands of feet. So by just putting a 10 there, then that's appropriate, because that represents 10,000 feet runway.
So do you divide by 3, and then
Correct.
3 plus 3, 3, whatever. And do you divide that by log or what?
Okay. Yes, that's where, no you don't divide by log, but this is where this is the most common place to get stuck. Yes, we have a single log, and when we have a single log, write it, rewrite it as an exponent. Okay? So what's the understood base here? Correct. So this is really saying 10 to the 3 1/3 power equals x. And that would solve out, and what would that be telling you? That would be telling you the weight of the plane. That could go off of the 10,000 foot runway. That's not that heavy. So
2,100.
right. So I got 2,154.43 pounds. So that's going to be a really, I don't really know. I'm not experienced airplane person, but I would think that would be like just a little single rider person airplane. Okay. See? It's what? It's a little one. I mean, is there even airplanes that small? I don't know. Okay. All right. The last thing here is a Hornet that weighs approximately 14,350 pounds, empty, and we know that it can take off from a length runway of 7,000 feet. So actually, based on the problem we just did, we could probably tell that this does not follow the same model as all those other ones. You think that this is an airplane to which our model applies. Remember our model being the length of the runway in thousands of feet is equal to 3 log x, where x is the weight of the plane. So that's saying a 7,000 feet runway would support this right here. And so you just need to see if that's true. So this ends up, if I did my calculations right, 12.4706.
About 13, I mean 3. Oh, it's 5.
I just put into my calculator 3 times.
Oh, I did 14 points.
Okay. 3 times log 14,350. And so that is 12. So that's saying that according to this model, our airplane that weighs 14,350 pounds would need 12,471 feet of runway. But this Hornet apparently is special because it doesn't need 12,471 feet of runway. It only needed how much? 7,000. So does the Hornet, this F-18 Hornet, does it use the same model that are all of our other planes that we talked about? No. So no, because it only needs 7,000 according to the model. It would say it would need 12,400.
Why wouldn't you divide by the 3?
Okay, question is, why wouldn't you divide by the 3? Well, I mean, I guess you could. If you did that, if you said, you know, typically what you divide by 3 if you're solving for something. But all that would do, dividing by 3, would just be saying, okay, is log 14,350 equal to this number here, which is 2 1/3. So then you would just be saying, I mean, all you're still doing is seeing if these two sides of the equation are equal. Okay? Alright, so that's all the notes